And welcome to part 4 of the proof of the Lucas-Lehmer primality test. In this video, we are going to prove a very important theorem, which I think is quite complex. So this video may be a little longer, maybe it'll be a little shorter, I don't know, but I think it may be a little longer. So this theorem that we're going to prove, it's necessary to prove the theorem that this entire video series is about, the Lucas-Lehmer primality test. So this is a smaller theorem, still very big and impressive though, so I may do multi-videos about it, I don't know. I'll decide later. And we're going to use this this theorem to prove the primality test. Okay, so this theorem involves groups. So first I'm going to define what a group is. So a group, if I have a bunch of numbers, right? So say I have like some numbers and I write them down, okay? And then I have some sort of operation on those numbers. So what this means is I have a list of numbers, right? Okay. And this is my set of numbers. If I pick any of two of those numbers, I can basically do some operation, okay? Which I will represent with a multiplication symbol. It's not the same as multiplication. It's just some operation that will produce a new number, okay? But since, I don't know, there's not a lot of good symbols, I'm going to use multiplication. So basically, if we have some list of numbers, right, so say we have some numbers, right, this is a set of numbers, and then if I take any two numbers in that set, right, this is going to give me a new number. Note that this multiplication symbol does not mean the times. I'm not multiplying them. This is just some new function that I'm defining. So there's a few rules about a group. So for a group is a set of numbers equipped with some function that basically you can take any of those two numbers and you multiply them. So there's, I think, 4 requirements for a group. So first of all, if I take any two numbers in my group and I apply the function to them, I'm going to say multiply them. It's not really multiplying, it's doing some other function. So I have some function, I apply the function to them. Think of it sort of like multiplying, except it's not really technically multiplying. Okay, and then I get a new number. That new number, that is the output, has to also be in my set. That's called closure. So, for example, if when I did my function, note that this is, again, this is not multiplication. This is some other function. When I do this, if it was like 36, 36 is not in my set, so therefore that would not be allowed. Okay. So the second thing, is that, So the second thing that we have is that we have something called associativity. Okay, so here, I'm going to give an example of that. And I'm also going to write down the rules as they come. Okay. So here. So if I take 7 times 44, right, and I multiply it by 28, although it's not really multiplication, just remember that, that has to equal 7 times 44, 7 times and then this thing. So it doesn't matter if I do this one first and then that one, or this one first and then that one, okay? It does not matter. They have to be equal to each other. As such, I don't even, so therefore when I'm writing this, I'll never have to specify which one I do in which order, because it doesn't matter what order you do them, it's all like the same. So this is called associativity, this property that it doesn't matter which one I do first, like that. Note that this is not commutativity, which means 7 times 44 does not have to be the same as 44 times 7. Again, I'm just going to say again, it's not really times, it's not multiplication, it's some function. 7 times 44 does not have to be 44 times 7. So it does not have to be commutative. If you switch them, it could give you a different answer. That doesn't matter, but it has to be associative. It doesn't matter which ones you do first. If you do this one and then add that one, or those two first and then add that one, it does not matter. It has to be the same. Alright, so next we have, there has to be a special number in my set, called It's the identity. So you know how if you multiply any now I am talking about real multiplication for a second. So you know how if you multiply any number by 1, it stays the same, right? Like 64 times 1 is just 64, right? So that means 1 is like the identity element, or I'm not sure exactly what its name is, but a group also has to have one of those. So that means one of the elements are in this set. No matter what, like if let's make it 1. If I take 1, and I multiply this. Now I'm talking about the group thing. It's not real multiplication anymore. So if I multiply 1 by anything, it has to give me that anything. And that means 1 is an identity. It's like the identity element. Now I'm just gonna give you a really quick proof. You cannot have 2 identity elements. So if I had 2 identity elements and I multiplied them by each other, what do you think would happen? Now, what would happen is, because the definition of an identity element is that it has to be the other one that it ends up being. So this one would be like, hey, you're the answer, and this one's like, hey, you're the answer. They can't both be the answer unless they're the same, so there can only be one identity element. If you don't understand that, all I'm saying is there cannot be more than one identity element. So yeah, so there's exactly one element. When you multiply anything by it, you get that thing. And 4 inverses. Okay. And in inverse, this means. Alright, so inverse is right here. What this means is that if I have something in my set, there has to be another element somewhere in my set. And when I multiply them, I have to get that identity. So, just to summarize, the 4 things you have to have: closure, and I'm going to say multiply. It's not really multiplication. When I multiply any 2 elements, it has to give me a third element that's in the set. Associativity. It doesn't matter if I do 6 times 4 times 5 or 6 times 4 times 5. Note that 6 times 4 does not have to be the same as 4 times 6. Identity. There has to be one unique element in your set. When multiplied by anything, it has to give that thing. There cannot be 2 by simple logic that when you multiply them, it would be impossible. Okay, and then 4 inverses. Each element in your set has to have another element that when multiplied will give you the identity. Okay, so those are 4 properties of a group. So now let me think. Should I? Yeah. So let's get into a little of the group theory. So one thing you might be thinking. So if I have some. One thing you might be thinking is if I have some like numbers, like what's a good example of a group. So I'll show you one example of a group. So you know how if you have like a number like 77, right? And you take away 5's repeated, like you divide, you have a remainder, right? That 77, when you divide it by 5, you have a remainder 2. So what this means? Sorry, if I'm doing 5, I shouldn't have that. So basically, what this means is that you basically, I can write down a list of all the remainders when I divide by 5. It would be 0, 1, 2, 3, and 4, right? So those are the only possible remainders when I divide by 5. So what happens? So if I add, so basically, if I add 2 of those, it's very interesting. So basically, if I have this is my list of remainders modulo 5, right? Or the remainders you can get when you divide by 5. When you divide a whole number by 5, right? 0, 1, 2, 3, or 4. Now, how I'm gonna define addition. Basically, if I take 2 and 4 and I add them, normally I get 6, right? But 6 is up here, right? But because this is all about the remainder when you take 5 away, or right, it's sort of the same as 1. So therefore, 2 plus 4 is 1. You should like next time you're in like a math room, you should just yell 2 plus 4 is 1, and it would be funny. Anyway, so basically, yeah, and similarly, 3 plus 4, that's 7. Its remainder modulo 5 is 2. So you can check this as a group here. So I'll show you that's a group. Any 2 of these elements, no matter which 2 I choose, I'll add them, and I'll take the remainder modulo 5, and it'll be one of these, because these are the remainders modulo 5. So we have closure. Associativity. It doesn't matter if I do 2 plus 3 plus 4, or 2 plus 3 plus 4, right? I mean, that's just basic property, like addition. It's not affected here. Identity. 0 is the identity element in this case, because if I add 0 to anything, that anything stays the same, right? Like 0 plus 3 is 3 in this group. Inverses. Every number here has an inverse. 2's inverse would be 3, because when you add 2 to 3, you get 0. Right. And 0 is identity. 1 would have an inverse of 4, because when I add 1 and 4, you get 0, and 0 is identity. So that is an example of a group. So now one question you may have is, what if I was to take like a group, right? So say I have a group, right, of some elements, and then I take a subgroup. What this means is, like, if I have some elements and then I have an operation, what if I take only some of those elements, and then that's still a group? And now the theorem we're going to prove in this video is that the number of elements in that smaller group must divide the number of elements in the bigger group. So I'm going to restate that. If I have a group with some elements, and then a smaller number of those elements inside that list of elements just by themselves also form a group, then the number of elements in that smaller group must divide the number of elements in the bigger group. And so this is what we're going to prove. So, and I think that the proof is pretty complex, but once you get it, it's like really nice. So let me see, how should I start? So one thing we're going to do is we're going to define something. So say we have a group G, okay? So this is our group. What this means is just a list of some elements, right? And it has some operation, we'll call it multiplication, and like any of the two elements in G, when you multiply them, you get another element in G, and it has all those properties we talked about. So I have some group G, okay? Now, there's a subset, which means like a smaller, just part of G. Like if G contained the elements 3, 5, 11, 17, 11 and 17 would be a subset, because it's contained in G. And let's call that subset H, and say that H also forms a group. What? So not only is G a group, but H is also a group, and very importantly, all the elements in H are contained in G. So what we're going to try to prove is that the number of elements in H divides the number of elements in G. So, and it's very nice proof. It's very good. So I think I'll be able to get into this video. It's going to be a pretty long video. If I do, maybe I'll decide to do another video. Regardless, it's really cool. So let me think. So if first, what we can do is we can define sort of something called an equivalence relation. So basically, say I have like two elements in G, right? Say there's some, but I'm not sure if I've exactly explained this, but when I say an element, I mean like something in it. Like an element of G would be some number that's in the set G, or in the group G, sorry. So say I have two elements A and B, okay? Now I'm gonna relate them. Basically, we'll say that A is related to B, okay? Okay, and so, and if and only if, basically, here, I'll come explain this in a while. Okay. Alright, so this may look a little intimidating, but don't worry, I'm going to explain it. So, what this means is I have my group G, right? And then some of the elements inside my group form a smaller group called H, right? Now I have A and B, some elements in my group G, and I'm going to say they're equal. They're not, like, this is just some special thing, sort of like equal I'm defining. That's why I'm not using equal sign. They're equal. I'm going to call it quul. I'm going to call it quul. It's like equal without the E. This is not official. This is just something I made up on the spot. So A and B are quul, okay? If A equals B times H for some H in capital H. What this means is I say that A and B are quul like A equals B. If when you use I shouldn't write BH. I should write B times H. If for some H, there's some element in this small group that when I multiply it by B, I get A, right? So A, so basically, let me try to restate this really simply. So I have a big group G, and inside I have a small group H. Now I'm saying for any two elements in G, I call them quil if the first one is equal to the second one times some element that is in H. Okay? So we can get a few properties from this. So our first property we can get is if A equals B, then B equals A. So I'll show you how you get that. All right. Alright, so basically if we say if there's this relationship between A and B where A is equal to B times H for some H, then if B has the same relationship with A in the other order, that just means B is equal to A times H for some H in it. Okay, so here's the thing. If we choose this, so here there's some H in some lowercase, some element in our group H that when multiplied by B gives A. Okay, so we have A is B times H, so I can substitute that in here. Alright, except here. So, okay, so basically I'm going to set these to be inverses. So what this means is, if this is true, okay, if A equals B, right, what that means is A is equal to B times H for some element like H of the group H, right? There's some element that when I multiply B in it, I get A, right? Now, what this means is basically what I'm going to try to prove is that means B is equal to A times H for some different element in the group H. Okay, so what I'm going to do is okay, so what I know is A is equal to B times H. So, and I'm going to call this one H1 and this one H2, okay? Yeah, if you haven't done group 3 before, this may be a little confusing. Just try to stick with it. Even if you don't get the group 3 part, you can watch all the other parts and still get a decent understanding of this stuff. But yeah, if you do get it, it's really cool. So, so basically we have, this one's H1, right? So there's some element H1 in the group H that when I multiply B by it, I get A. And then I want to prove that if this is true, then there must be some second element H2, right? That when I multiply it by A, I get B, right? So what if I said, remember how every element has to have an inverse, right? Which means every element has to have some other element. When I multiply them, they become the identity, right? So I'm going to choose H2 to be the inverse of H1, and you'll see why. Okay, so let me think. Yeah. Alright, so let's say H2. Alright, what this means is H2 is equal to the inverse of H1. So I have an element H2 and I have an element H1, and H2 times H1 is the identity element. So up here I said that A was equal to B times H1. So therefore I can substitute it into here. Right? So I just substituted it in, right? Now, because associativity, this is just B times H1 times H2, so I could also take B times H1 times H2, and I could do this one first. So I'm going to write that. Alright, so I have this. I'm shutting my door really quick. Give me 1 second. Okay, so right. So, but remember, H1 and H2 are inverses. So when I multiply them, it's the identity element, right? So this right here is the identity element, and then I'm multiplying it by b, and by definition, anything multiplied by the identity element is itself. So therefore, b equals b, which is obviously true. So therefore, if a equals b, then b equals a. Okay. So next, we're gonna prove. Okay, so next what we're going to do is we're going to prove that any element is equal to itself. Alright, so that's the second step. So I'm going to prove for any element it is equal to itself. And this part's sort of simple. What I'm going to do is I'm going to choose my h value. Remember, what this means is that a is equal to itself times some element in h. But since h is a group, it has to have an identity element, which means that it has to be so I'm going to choose that one, which means it's itself times the identity. And anything times the identity is itself. So this is obviously true. And this video's gotten long enough, so I'm going to stop this video now. Thank you for watching, and I hope to see you in the next part. Goodbye.